What's up, everyone? Today we're talking about chemical compounds, and we're going to be looking at the bonds, the type of bonds, the formulas, how to make chemical formulas, how to name those compounds, the structure, the polarity, and the geometry. Now, going back, we learned about atomic representation, right? So we learned about atoms by themselves, and we learned about how you represent them, right? So we know the ball structure that looks like this. This is sodium, right? The Lewis structure, which shows us the valence electrons, right? We know the electron configuration that shows us the orbitals, the s and p and d, and then the atomic box that shows us how those electrons are organized, right? So after looking at that, we want to know, okay, now that you know how one atom is, how does it combine to another atom? And knowing these characteristics is crucial to knowing how the atom will bind. We learned about how valence electrons and the Lewis structure is going to be crucial, and we're going to see why in a minute. All right, so let's start by talking about chemical bonds. What is a chemical bond? A chemical bond is easily a lasting attraction between atoms, ions, or molecules, right? And this enables the formation of chemical compounds. So it's pretty much the attraction, the binding between two atoms. And this is a binding that's lasting, meaning that stays there, right? We call them chemical bonds. So we talked about how binding is dependent on valence electrons. And you remember that the valence electrons are the electrons on the outermost shell. This is an example of an atom that has 20 electrons and protons. What's that atom that has 20 electrons and protons? If you look at your periodic table, this is going to be calcium. Calcium, when you represent the Bohr model like this, you're going to get to one electron on the outside, right? So it's going to be one electron. Not actually one electron, never mind, two electrons on the outside, right? So the first one gets two, the second one gets eight, the other one gets eight, and then on the outside you get two electrons, right? So those are the valence electrons. So the Lewis structure represents only the valence electrons on the outside of the atom. So I gave you this really nice table that has all the Lewis structures that you need, all the Lewis structures of the atoms that we're interested in. Now, as you can see, the Lewis structure on the first group has what? It has one electron on the outside. The second group, two electrons. The third group, three electrons. The fourth group, four electrons. The fifth group, five electrons. Six, six electrons, seven electrons, and eight electrons. So it's easy to remember, but you have to remember that. But you don't have to remember all of them. You just have to remember the Lewis structure on each group, right? And this is going to help us. Another thing that's going to really help us is remembering the charges, right? And the charges come from the Lewis structure, right? Remember that a charged atom, an ion, is an atom that has either lost or gained an electron, right? A positive ion has lost an electron, a negative ion has gained an electron. And look at this. The elements on this side tend to lose electrons because they just have just few on the outside, right? So if it has one electron, it loses it and it becomes plus one. So I would, if you get a quiz or an exam and you get a periodic table, just write on top these charges, write these charges on top, and even you can even write representative Lewis models so that you can say, oh, this one electron, two electrons, three, four, five, six, seven, eight. That way A lot of questions they're going to ask you. You're going to use the Lewis, you're going to use the charge. And how do you use that? Let's say you have H2O, right? This is a molecule, a compound of water, and it's oxygen bound to two hydrogen atoms. How does that happen? Why do we need two hydrogens on oxygen? Why not four hydrogens? Why not eight hydrogens, right? What determines that? If you look, another one is like Na2Cl. Is This is salt that we use. Why just NaCl? Why not Na2Cl like hydrogen? Well, the rule goes back to the valence electrons, right? If sodium here, for example, has one electron and fluorine has seven electrons, these seven electrons are arranged so that fluorine only has one free electron. The other ones are pairs. And these ones that are pairs are not going to bind. So only this electron is the one that needs one more. So what happens? Sodium gives its one electron to fluorine. It's a one-on-one relationship. But here, oxygen is going to need two because it has two free electrons, right? But we'll talk about the rules of that later. One of the main rule is called the octet rule, which says atoms gain, lose, or share electrons to fill their outermost shell. So for example here, sodium lost an electron so that the outermost shell has 8 electrons. Fluorine gained 1 electron so that the outermost shell has 8 electrons. We'll come back to the octet rule later. But there are two types of bonds: ionic bonds and covalent bonds. I need everybody to know how to tell the difference between the two. It should be very obvious. The ionic bonds are bonds between metal and non-metal. Metal and non-metal, right? Remember the table that we looked at here, right? Remember this imaginary line that you're gonna have. Everything blue on this table is metal, so everything yellow is not metal, right? So it's these elements on this corner and hydrogen. These are non-metals. The blue are metals. So a combination between the metal and non-metal is an ionic bond. And this involves the transfer of electrons from one atom to another. It's very, very important. And it produces what? It produces ions, right? So when one thing loses an electron, it becomes ions. Now the covalent bonds, on the other hand, is between a nonmetal and a nonmetal. So here it's between elements. Those yellow elements you see. You see those yellow elements? Those are the ones that involve covalent. So these elements right here. These elements right here. I can't write. These elements right here are going to form covalent bonds, and then hydrogen here as well. So a bond between these elements is going to be a covalent bond. And this bond is going to involve sharing of electrons as opposed to the transfer of electrons. They are going to share them, and they don't produce ions. So three main differences, three important differences that we're going to talk about. So let's start with the ionic bond. If you have NaCl, the sodium that has one electron is going to give it to chlorine that needs one electron. This is a transfer of electrons, and Na is a metal, Cl is a non-metal, right? Na is around here is a metal, Cl is a non-metal over here, so it's an ionic compound, right? Metal, non-metal, transfer of electrons, and third characteristics, they give rise to ions. So when sodium loses an electron, it becomes Na plus. It's an ion. When chlorine gains an electron, it becomes chlorine negative. It's the chlorine that has gained ions. And look at this. They both have 8 electrons on the outer layer. This is the fulfillment of the octet rule, right? So the reaction is really like Na plus Cl becomes NaCl, and this NaCl is really Na plus and Cl minus. All right, this is an ionic bond. All right, so another characteristics of ionic bonds is that we looked at the size of atoms, right? What happens is when sodium or when a positive when a metal loses an electron, it becomes smaller, right? It becomes smaller because it just lost a layer. When an element gains an electron, it becomes bigger, and that change in size makes them pack in a compact arrangement that we call crystals. So ions tend to form crystals. So this is NaCl, this is Na and chlorine, right? And those crystals are arranged in a nice cube. And there are different types of crystals. We won't talk about it, but there are different types and different structures of crystals, and you can see a cube of salt as well, even on a bigger scale. You can see that it arranges really nicely. It's because these are ions, right? So remember that these are going to do that, and remember that the ions form based on the charges, right? So these are cations and anions. Remember that cations are positive ions, anions are negative ions. So what about a covalent bond? We talked about how a covalent bond is between a non-metal and a non-metal. So what happens here is that there is no transfer of electrons. Let's see another example. There is no transfer of electrons. If you have an H2 bond, right, an H2 compound, there's no transfer of electrons. These two hydrogens will share these electrons. If you have O2, right, oxygen, they will share 2 electrons. There is no transfer of electrons. It's very weird, but it's different, right? So let's say, for example, look, you have hydrogen. Let's get an example. You have hydrogen that has 1 electron. You have chlorine. Chlorine has 7 electrons. So we're going to do the lowest structure of them, right? So we saw that NaCl during in NaCl, Na gives away its electron, but these ones, they don't give them away. They just share, right? They share between each other. And when they share, it's a covalent bond between a nonmetal and a nonmetal. There is no transfer. And since there's no transfer, there are no ions, right? This right here is a covalent bond. Two big differences between the two, all right? So something weird happens in covalent bonds. So look at this. If you have a covalent bond between, let's say, oxygen and oxygen, right? Oxygen and oxygen. Oxygen has 6 electrons on the outside, right? 6 electrons. Another oxygen has 6 electrons, right? A bond between them, and actually they make 2 double bonds because they have 2 free electrons. These bonds right here are equal bonds, right? Because they just oxygen versus oxygen, right? Or H2 hydrogen versus hydrogen. It's just one bond that's equal. They're sharing these electrons equally, equal sharing of electrons. But what if we have, for example, H and Cl? They're still sharing electrons, but this is not the equal sharing. Cl is pulling more, right? So it's still a covalent bond, but it's a covalent bond that we call a polar covalent bond, right? So if you have hydrogen and fluorine, for example, look at how fluorine looks like. Look at how hydrogen looks like. They are still both nonmetals, so it's a covalent bond. But look, hydrogen has one lone electron. It's ready to give it. It won't give it away, but the sharing won't be equal, right? So we're going to share this electron, but the sharing won't be equal, right? So here the fluorine that's bigger will be pulling more than hydrogen that's smaller. And that's what we call polar covalent bond. So a polar covalent bond, we like to represent it this way, right? So this is HF, this is HCl, and this is the polarity. The polarity is an unequal sharing of electrons, right? So HF and HCl are polar covalent bonds. They are not only covalent, they are polar covalent bonds, right? And we represent the polarity this way, right? We represent it this way. So these signs right here are partial positive and partial negative. So even though these are not positive and negative, but they have a partial negative and a partial positive charge because fluorine is pulling, H is pushing, right? It's a partial negative and partial positive. And we make an arrow this representing polarity. So an arrow that looks like a plus sign here represents polarity and it points towards the element that's pulling more, right? And these two, positive and negative, we like to call them poles, right? Positive and negative pole. So that's why sometimes somebody will say that this is a dipole, right? Now, how do we tell which element is pushing and which element is pulling, right? We use electronegativity. What is electronegativity? Electronegativity is a measure of the ability of an atom to attract electrons in the chemical bond. So it's an ability to pull, right? So as you imagine elements with a high electronegativity, they will have a high ability to attract electrons. So guess, in H and F, which one has a higher electronegativity? It's F, of course, right? F is pulling, is attracting electrons, and H has a lower electronegativity. So look at this. We have a table of electronegativities, and what ends up happening is it increases as you go up this way and as you go to the right, as you go up to the right on the periodic table. So that means that the elements in the corner right here have the highest electronegativity. They are really, really high. N or F have the highest electronegativities, right? So that's why these nonmetals tend to be high, have a high electronegativity, right? So now that you know electronegativity, you can say, okay, something that has a difference in electronegativity is polar. But not only that, you can measure the polarity if you know the numbers, right? So if I ask you what's the polarity of HF, well, you can just take the electronegativity of F, which is high, minus the electronegativity of H, which is low. And the difference will be the polarity. And if you know the polarity of two molecules, you can say, oh, one is more polar than the other because it has a bigger difference in electronegativity. So between H and F, right, the difference is 1.9. But between H and Cl, the difference in electronegativity is 0.9. So HF is more polar, right? That's the polarity. So there are differences in covalent versus ionic compounds, and we talked about these. Um, They are made of metal and non-metal, the ionic compounds. Covalent compounds are made of non-metals. The electrons are transferred versus shared, right? In a physical state, we say that ionic compounds tend to be solid and they tend to form crystals, right? It's a lot of salts, a lot of powder. Covalent can be any. Some are salts, some are gases, some are liquid like water. They can also be crystals as well. Covalent are more varied. Ionic dissociate in electrolytes or ions. Whenever you see electrolytes, think of ions. And covalent don't. And another really important point is that ionic compounds, because they are stronger and they get together, they are higher. They are harder to melt and boil, so they have a high melting and boiling point, right? And that's enough for the covalent and ionic bonds. So let's talk about how you write in a formula, right? How do you write formulas, right? Now, first of all, what is a formula? A formula, a chemical formula, is something that so you will see, compounds be written like H2O or NaCl, something like this. That's a chemical formula. So it's going to have a compound, right? Like it's going to have an atom. So let's say an atom A that has a certain number here, like X, and an atom B that has a number like Y. And A and B will be atoms, X and Y will be the numbers of those atoms. That's the chemical formula. So it's a representation, right, of the fundamental compound using chemical symbols and numerical subscript, right? So if you have H2O here, what we're really saying is that we have two hydrogen atoms bound to one oxygen atom. It's a very easy way to represent what's happening in a compound. All right, so why do we have two here? Why not three? Again, it's because oxygen has two vacant electrons and hydrogen has one. So if you give one hydrogen, it's going to need one more. That's why we need two hydrogens and you get H2O. But you can't always draw this in order to find a formula. There is an easier way to find a formula of any compound, and that is what I call the cross rule. What is the cross rule? Before we know the cross rule, we need to know the charges of our compounds, right? Remember the charges, you gotta always know the charges. But after you know the charges, the cross rule is all you need. And let me demonstrate. So let's go back to H2O. If I ask you what's the formula between hydrogen and oxygen, right? All you have to do is first put down the charges. So going back here, hydrogen has H plus, oxygen has minus 2. So plus 1 and minus 2. Those are the charges. The cross rule is a cross. So you make a cross between two of them. And what's the formula now? Is H gets 2 and oxygen gets 1. That's the cross rule. Isn't that great? Let's do another one. What if I give you aluminum and oxygen? Doesn't matter. Go back. Aluminum has plus 3, oxygen has negative 2. You do the cross. Now you know that aluminum will get 2, oxygen will get 3. That's the rule. What about calcium and chlorine? The charge tells us that calcium has plus 2, chlorine has negative 1. You do the cross, you say calcium Cl2, right? That's the cross rule. And now, this is an example examples that you can use to practice. You can just go ahead and pause this video and practice, but it's the same idea. You can now predict the formula of any two atoms, between any two atoms. All right. Okay, let's go to the next one. We're going to learn how to name compounds. Now, there are two different rules for naming depending on what compound we're looking at. So if you have an ionic compound, there's a rule. If you have a covalent compound, there's a rule. They will be very similar, but there's one important difference. Let's look at it. Let's start with ionic compounds. When naming ionic compounds, and remember the ionic compounds have a metal and a non-metal, right? And usually in the formula, the metal starts. So all you need to do while naming is you start with the metal, right? In this case, it's sodium. The second one is chlorine, right? But instead of saying chlorine, you have to use what we call a suffix, right? A suffix. So instead of saying chlorine, you use an IDE suffix. And suffixes, remember, it's the group that goes after, as opposed to prefix that goes before. So IDE is going to be, for chlorine is chloride, for oxygen is oxide, for sulfate is sulfide. So again, this is for non-metals. So these are, I think, most of the non-metals that you're going to use, and these are the suffixes of them, right? So chloride, fluoride, hydrogen is hydride, iodine is iodide, nitrogen is nitride, oxygen is oxide, phosphate is phosphide, sulfur is sulfide, right? So after you know these, you can name any ionic compound, right? Magnesium nitride. One really, really important distinction that you'll notice is that we're not caring about the numbers, right? We're just naming, disregarding the numbers. When you're naming ionic compounds, you don't put in the number, right? One more, let's go like one more level when it comes to ionic compounds. There are monoatomic ions. We've been looking at monoatomic ions, and these are ions that only have one atom. But there are things that we call polyatomic ions, and these are ions in nature that are in groups of atoms, but they act as one ion with one charge, right? And we're going to need to know them, especially these 9 that are highlighted. These are the most common polyatomic ions that we find in nature, and we're going to use in the lab most of the time, right? So we need to know them, and we not only need to know their symbol, we need to know their names and their charges. But after you know the polyatomic ions, and I ask you, okay, what's this? What's the name of Na2SO4? You'll know that this is an ionic compound that's made of this polyatomic ion, and this is sulfate. So this is going to be sodium sulfate. Now look at this. Where did these two come from? Well, you can do the cross rule and find the formula for polyatomic ions too. So if you already memorized that SO4, so if I ask you, oh, okay, write down the formula for sodium sulfate, you're like, okay, I'll do the cross rule. Sodium has +1. SO4 2 minus, it has -2. It's in the name, right? For each one of them, you'll see that they have a charge in the name, right? So if you have this, then you do the cross. The cross tells us that Na gets 2, SO4 gets 1. That's how you do the cross for polyatomic ions. Sometimes you have to put a number on the polyatomic ions and you have to put in a parenthesis. How does that look like? If I ask you, for example, calcium and OH, called calcium hydroxide. The hydroxide group has a negative charge, so it's a -1. Calcium has what charge? Going back to our charges, you find that calcium has +2. If you do the cross, you see that calcium gets 1, OH gets what? It gets 2. And remember, all of OH will get 2. So this group right here will need to be put in a parenthesis and it will get 2. Beautiful. So now you not only know how to do formulas and naming of monoatomic ions, but you know how to do polyatomic ions too. But make sure that you go through these and remember them. So these are examples to name these compounds. And again, if you remember them, you'll see that this is ammonium chloride, this is barium sulfate, this is iron nitrate, right? And copper bicarbonate. And for iron and copper, we'll talk more about it, but for what we call transition metal element, you put in parentheses the number of charge because the charge for iron and copper can be 2 or 1, but we'll look at that in another video. But this is calcium hydroxide, right? So this is how you name these compounds. These are ionic compounds, but you have polyatomic ions. All right, so after, now that we know that, I can also give you a name, right? I can give you a name and then I ask you a formula. So if I ask you, oh, barium chloride, and you tell me, give me the formula, oh, you know that it has barium, Ba, you have Cl, right? And then you go back to your charge, you know that barium, right? Barium is on this level. So barium has +2, right? And chloride is -1, right? So barium is +2, chlorine is -1. By the way, you don't have to know the charge of barium, right? As long as you know the charge of magnesium, for example, you know that all of them are going to be the same. And then after that, you do the cross, and after you do the cross is barium chloride 2, right? So you can do it back and forth. I can give you a name and ask you a formula, or I can give you a formula and ask you for a name, and you can do that. And go ahead and practice for this. So pause and practice. Now, how do we name covalent compounds? Right? Covalent compounds, naming them is the same way. The only exception is that we have to add a prefix, right? So instead of adding, we still add the IDE suffix like the other ones, but you also add a prefix. A prefix goes at the front, right? And the prefix that you use is going to be a number. So here we're going to add the number of atoms, right? It's very important because in the ionic compounds, we disregarded them. We disregarded the number of atoms, but here you need to include them. So if you have SiO2, you need to first see, oh, is this an ionic or a covalent compound? This is a covalent compound. If it's a covalent compound, you have to include the number. So this is silicon dioxide, right? This is dinitrogen pentaoxide. This is carbon tetrachloride, right? This is iodine heptafluoride, right? So it's the same idea, same rules. It's just that we got to include the number. And the beauty of it is that now that the name for covalent compounds includes the number, then to write the formula is easy, right? Because it's in the number, it's in the name, right? Nitrogen monoxide is, well, NO, right? If it was more than NO, they would have included it. Dinitrogen tetroxide is N2, N2O4 because it's tetroxide. Can also call it tetraoxide, right? So it's easy to write the formula when you have a covalent compound, but you have to be able to tell, is this covalent, is this ionic? And remember, if it's a non-metal and a non-metal, it's covalent. If it's a metal and non-metal, it is ionic, right? So now that we know how to tell what type of compounds we have, now let's look at how you can draw the structures of these compounds, right? Now I'm going to give you a few rules to follow, right? And you can pause, take a screenshot or something like that. But the main important thing is to practice those rules, right? So I'm gonna give you an example. Let's say I ask you, okay, what's the Lewis structure for H2O, right? So the number one thing is you have to draw what we call the skeleton or the arrangement of molecules, right? And there are rules that we follow. The number one rule is the least electronegative atom goes to the center. The element with the low electronegativity goes to the center. The only exception to that rule is that hydrogen and halogens tend to be always outside, So, and this is because they only have one electron to give, so they are usually not in the middle. An easy way to tell which one is in the center is if you have just one oxygen and two hydrogens. There's no way that the hydrogens are in the center. It's two of them. So oxygen is in the center and two hydrogens are around it. So let's write the skeleton. Step one, oxygen is in the center. You have hydrogen here, then you have hydrogen here. All right. What's step two? Step two says count the number of valence electrons. So you give them their valence electrons and then you count them. So oxygen has 6 valence electrons. Hydrogen has how many? 1 each. So the valence electrons, say VE, is going to be equal to 6 plus 2 is 8 electrons. We have to make sure that these electrons are accounted for in our structure, right? So that's the second step. The third step is here to fill the molecule with all the valence electrons. We did that. And then you connect the free electrons together to form bonds, right? So we're going to connect these electrons together. So the free electrons means the electrons that don't have pairs in them, right? So these will form the bonds and these will form bonds, right? We just made a bond. It's pretty easy. We're pretty much done. But after you do that, you're going to have to count electrons to make sure that you have added all of them, right? Sometimes you have extra electrons. Sometimes you will make a bond and you will see other extra electrons around that. You got to make sure that every electron is accounted for. So you have to count electrons to make sure that you have used all of them, right? If you have extra electrons here, sometimes you're going to have to make a double bond, and I'll give you an example in a minute. But you have to do that. The last step is I like to tell students that, just write a clean version where you say, oh, this is oxygen with two pairs of electrons bound to hydrogen, like that. That's the Lewis structure for H2O. So let's say you have CO2. Same thing. Carbon in the middle, oxygen on the outside. Carbon has 4 valence electrons. Oxygen has 6. One, two, three, 4, 5, 6. So it's 16. So valence electrons, if you add them up, are going to be 6 for hydro of one oxygen, 6 for another oxygen, that's 12, and then carbon is 4, that's 16 electrons. You gotta make sure that they are accounted for. So here, as you can see, one electron is going to bind to another, and one electron is bind to another. But look at this, we are not done, right? We're not done. There are more free electrons. This is one. There are more free electrons on oxygen and on carbon, right? So if you're not done after you made one bond, you know that, oh, I need to do another bond. I need to do a double bond, right? So then you know that you need to do two bonds, right? So you can see that this one can connect with this one can connect with this, but since this is gonna make a mess, you can just go back and say, okay, let's, you have these right here, you can say, oh, this one, let's connect this one to this one to this one to this one to this. It's two double bonds, right? And that's why I say after you're done, you make a cleaner version of this when you say COO like that. Then you have two pairs. You always have to include your pairs. And this is a Lewis structure for CO2. There's something that I forgot to mention. I mentioned it earlier, but I need to emphasize it. Whenever you have a Lewis structure, you have to fulfill what we call an octet rule, right? Remember, the octet rule is that every atom should fulfill an octet rule, which is a rule that says that, let's go back to it, the octet rule says that atoms gain, lose, or share electrons to fill their outermost shell with 8 valence electrons. That's the octet rule. So here, as you can see, oxygen is a covalent molecule, so it's sharing. So oxygen usually has 6 electrons, but look at this. It's sharing one more electron with hydrogen. So it's fulfilling its octet rule by sharing this electron with hydrogen. So it's 1, 2, 3, 4, 5, 6, 7, 8. Here, carbon usually has 4 electrons, but it's sharing other 2 electrons. So each of these bonds is counted as 2 electrons. So it's 1, 2, 3, 4, 5, 6, 7, 8. And oxygen is the same thing, right? It has 1, 2, 3, 4. Each bond is 2 electrons, so it's 5, 6, 7, 8. So we have to fulfill the octet rule. We have to make sure that we fulfill the octet rule. Now we've seen these covalent compounds, but let's do a ionic compound, right? So aluminum chloride 3. So same thing. What goes in the middle? Aluminum, and then 3 chlorine on the outside. And second step, give them their valence electrons. It's 3 for aluminum, chlorine is 7, remember? And the way I'm arranging this, by the way, is I make the free electron face aluminum because I know they're going to bind. Chlorine has 7, and I'm making the free electron face aluminum here. There you go. And now we have all the valence electrons. This one is easy because you can see that, oh, this electron goes here, we made a bond here, we make a bond here, we make a bond here, boom. Are we fulfilling the octet rule? Yes, because in ionic compounds we have a transfer of electrons instead of sharing. So in chlorine is, this electron is getting transferred to chlorine to get 8, right? And for aluminum, aluminum is losing all 3. And guess what? When aluminum loses all 3, is going to have the next layer that has 8 electrons. So we're fulfilling the octet rule for aluminum and chlorine as well. So if you have to write down a cleaner version of this, it's just Al bound to Cl, 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 and add the electron pairs. You can't forget that. Beautiful. All right, let's do one more. What if I ask you NH3? Same thing, N in the middle, H on the side, and H has 1 electrons, N has what? Can you guess? 5. So 1, 2, 3, 4, 5. And as you can see, hydrogens connect to each other. It's really nice. And the Lewis structure for NH3 is N connected to 3 hydrogens. Boom, 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 with a pair, an electron pair, right? Now, I said NH3 because there are exceptions, right? So I showed you polyatomic ions, and the first polyatomic ion I showed you is called ammonium, right? How do we make a structure for ammonium if we know that NH3 is the rule? We follow the same rules where, okay, you put N in the middle, you have H, but H, instead of having 3, now you have 4. All right, and next step is the valence electrons. So far so good. Valence electrons for nitrogen is 5, okay? And this hydrogen connects here, this hydrogen connects here, this hydrogen connects here. That's okay. But then you're like, okay, what do I do now? What do I do? Well, we have no choice but to break this pair. This is an exception. We have to break this pair and make a bond here. And when we do that, we have an electron that's extra. That's missing one electron. It's missing a friend. And because of that, that's why we have a positive 1 here. Because remember that positive means that we are missing an electron, right? And the way we represent this, the Lewis structure, we use brackets. So you have N with H hydrogens around it, and it has 1 electron here. You put it in brackets like this, and then you add a positive to show that it's a positive ion. This is how you do Lewis structures for polyatomic ions. Now you know. All right, so this example is for you to practice, right? By the way, another one that we didn't do is the diatomics, the atoms that have 2 of them. They are the easiest, because if you have H2, it's just hydrogen 1, it's 2 of them, right? If you have Cl2, chlorine and chlorine, chlorine has, remember, 7. This chlorine has 7, and I'm going to make it so that the free electrons face each other. And then look at this, 1 to 1. Sometimes you have something like oxygen. Oxygen has 6, and this 6, oxygen has 2 free electrons. And what does that mean? It means that these 2 free electrons get together and you get a double bond, right? So the Lewis structures for the diatomics are easy. This is O2. All right. So after this, right, after we learned about the Lewis structures, right? After we learned about Lewis structures, let's talk about the geometry, right? The geometry of this. Why does this matter? This matters because, for example, I showed you that if you have something like CH4 and the Lewis structure of CH4 is this, you see that this is a nice linear molecule on one plane. This is not the reality. It doesn't look like this in real life. In real life, meaning if you look at this molecule, it's going to be something like this with one of these coming out. So it's going to be something that we call a tetrahedral, right? And this is the real structure. And this structure is going to be a 3D structure. It's a geometric structure. And what's happening really is that these hydrogens, because they have energy, they're going to be pushing each other and they're going to rearrange where they're the farthest from each other, right? So because of that, you have a standard called VSEPR theory or valence shell electron pair repulsion theory, right? And we use this to predict the geometry of molecules based on what? Based on their Lewis structure, right? So for this introduction class, I want you to know 5 different geometries. And these 5 different geometries are pretty easy. Let me show you. If you have an atom, let's say the middle atom, let's call it X. You have a middle atom with A atoms around them, with no pair of electrons. This will form a line. So this is what we call a linear geometry, right? Linear. And then an example of this will be like CO2 or something like that, right? If you have an atom in the middle with 3 things around it, right? It's going to form something like a triangle, but we don't call it a triangle. We call it trigonal. Whenever you hear trigonal, think of a triangle. So trigonal planar, and it just means that it's a triangle and it's on a plane. It's on one plane. It's trigonal planar, right? Example is what I was showing you, like aluminum chloride 3, right? No electron pairs. If it's an atom connected to 4 different things, right? It's going to form what I was showing you guys, a tetrahedral, right? Tetrahedral. So CH4 is an example. Another example is SiH4, or I don't know, CCl4, all of these. And the main thing is there is no electron pair. It's a central atom with 4 things connected to it, right? Note that these 3 don't have any electron pair. What happens if you have a pair? If you have one atom in the middle, you have 1 pair or more, and then you have 2 things connected to it, these 2 things are going to be bent because the pair has energy. So it's going to kind of push them down. And this geometry is called bent or angled, right? Example, H2O. Right? Remember that oxygen has 2 pairs. You have hydrogen. The geometry is this. It's not linear, it's angled because you have pairs that are pushing the hydrogens, right? Another one is if you have one thing that has pair but it's connected to 3 things. If it's connected to three things, it can't be trigonoplanar, right? It can't be like a triangle like this. It can't be like a triangle. Why? Because the pairs have energy. They're going to push. These are electrons. So this one, we call it trigonal because it's three, right? Trigonal because it's three, but now it's no longer a planar, it's no longer on a plane, it's a pyramid, right? So a trigonal pyramidal, right? And an example of this is NH3, right? So remember when we did the Lewis structure, we have N has a pair, meaning that the hydrogens will be pushed down here and form a little pyramid of three. And these are the 5 geometries that I'm gonna need you to know. We don't need to know more than that. But there are many more. There are many more. There are things that are connected to. There's one thing that's connected to like 8 or 7 different things, and there are geometry for that. There are geometries when you have pairs and non-pairs, but we only, this is an introduction class, so we're only going to look at these 5, right? But for each atom that I give you, you should be able to tell what geometry it is, right? And this is another representation of what I was telling you. This is another representation from your book, but it's the same idea. One of the things that we also need to know is the angles, right? If you have a linear structure, the angles between them is 180. Trigonoplanar is just a nice 120, right? A tetrahedral is 109. The angle is 109 between all of them, right? Trigonopyramidal, the angle is 107 between them, and angular is 104.5 between them. And this varies depending on what type of elements you have, whether you have one or two pairs of electrons. As you can imagine, if you have one more pair, it's going to push even further, so the angle will be smaller, right? So I think that's enough about geometry. So this is an example of what you can do to practice. One thing that you'll notice is that before you figure out the geometry you have to know the Lewis structure. So for PCl, for example, P, you gotta know the Lewis structure for P and then Cl. So you have P, Cl, Cl, Cl. So what's phosphorus? What's the Lewis structure for phosphorus? How many valence electrons does it have, right? Those are the things that you gotta practice. But if you see here, P is in the same group as nitrogen. So if you know nitrogen, you really know P. And we already done nitrogen. So let's see, where were we? Here. So P has 5 just like nitrogen. So 1, 2, 3, 4, 5, right? And chlorine has what? It has 7. So the Lewis structure for this is going to be the phosphorus connected to 3 chlorine atoms, right? 1, 2, 3. But look at this. It has a pair. It has a pair. So it can't be trigonoplanar. What is it going to be? It's going to be just like NH3. It's going to be trigonopyramidal, right? Because it has 3 of them and a pair. So it's going to be a pair at the top here, P, and then the chlorines will be at the bottom, trigonopyramidal, right? So you can do that. And the same is for pH3, by the way. It's going to be P with the hydrogens down here, trigonopyramidal. SiH4, it's going to be Si connected to H4, and this comes from you knowing that Si has 4 electrons, 4 valence electrons. So after you do the Lewis, you're like, oh, it's connected to 4 things and it doesn't have a pair. What is that? It's a tetrahedral, just like CH4. So you're going to start recognizing these um, as you do as you do these examples, and also you always need to compare, right? So that's why I gave you examples here, right? Because if you know that H2O looks like this or NH3 looks like this, pH3 is going to look like that as well. NH3 is going to look at like pH3. All right, I think that's enough. Now, after you know the Lewis structure and geometry, then you can find the polarity of a molecule, right? Now, we've already looked at the polarity of a bond. So, a polarity of a bond is, if you have H here, you have F here, right? We know that the polarity of this bond between the two means that it's an unequal sharing of electrons, right? These two electrons are unequally shared, and we know that F is pulling more, so you can do an arrow with a plus sign to show the polarity. This bond is polar, right? So if this bond is polar, this compound is also polar. This is a polar molecule. And remember that we say polar when it comes to covalent compounds, right? We say that it's polar. But look at this. If you have something like CH4, right? CH is polar, right? Because they are difference in electronegativity. So this is a polar bond, this is a polar bond, this is a polar bond, this is a polar bond. But look at this. These polar directions are equal and opposite. And guess what happens? They cancel out. And when they cancel out, this molecule right here is non-polar. It's non-polar. Even though the bonds are polar, the molecule is non-polar. So depending on the Lewis structure and the geometry, you're going to have a polar or non-polar molecule. Now, I'll tell you real quick that if you go back to our structure, a linear molecule, even if the bonds are polar, it's going to be non-polar, right? A linear molecule is going to be non-polar. A tetrahedral molecule is also going to be non-polar because they're going to cancel out. A trigonoplanar molecule, if it's if it's a if it's a covalent molecule, is going to be non-polar as well because they're going to cancel out. Now, this is an ionic molecule. So when it comes to ionic molecule, we're not talking about polar or non-polar. This is when you're talking about covalent. That's when we say polar or non-polar, right? But these geometries that don't have an electron pairs tend to have non-polar compounds because they cancel out. But if you have a molecule like this, it won't cancel out. Look at water. The water polarity is going to look like this, right? It's pushing towards oxygen. It's pushing towards oxygen. But because you have a bent geometry, they are not going to cancel out. So this is polar because they are not going to cancel out. Same with NH3. It's pushing towards NH3 like that. But they're not going to cancel out because they are not pushing in opposite direction. So this is going to be polar as well, right? So depending on the geometry, something can cancel out and be non-polar, or they just can add up and be polar, right? So in addition to knowing the polarity in a bond, you got to know the polarity in a global compound, and they won't always be the same, right? Sometimes they will cancel out and a molecule will be non-polar, right? It's really important to remember. All right. So these are examples where I give you to determine the bonds, whether or not they are polar, and then determine the compounds. So SiCl, first, whenever you see a difference in electronegativity, you know that something is polar. So this is polar, this is polar. Oh, it's only non-polar whenever you have the same element. So this is non-polar, this is polar. But when it comes to compounds, it's not going to work, right? So oxygen, we know that oxygen is oxygen to oxygen, so there is no unequal sharing. So this one is non-polar, right? Non-polar. HF is, you know that it's H to F. We already wrote it down. HF is definitely polar because there's unequal sharing, right? This is polar. CH4, I already gave you an example. Even though CH is polar, CH4 will cancel out, so this will be non-polar. H2O, because it's a bent geometry, so oxygen is bent, and because it's bent, it's going to be, guess what, polar, right? So you can practice other examples as well. So from all of this, right, any two elements that I give you, any two atoms, you should be able to, number one, tell me what kind of formula they're going to make, right? And then after you get the formula, what kind of compound, you're going to tell me, is this ionic or covalent? That's number two. Number three, you should be able to tell me the name of that compound, right? Number four, you should be able to draw the structure of that compound, right? That's number four. Number five, you should be able to tell me the geometry of that compound, right? And number six, tell me the polarity of that compound, right? So we've learned about how to do all of that. Now, the last thing I'll talk about is the physical properties, right? How these things talk, relate to physical properties, right? The polarity, the geometry, all that stuff. How does it relate to some physical properties? When it comes to physical properties, I'm talking about um, melting points, boiling points, how soluble they are, you know, things like that, whether they tend to be solids or liquids. That's what we mean by physical properties, right? So where does physical properties come from? They come from intermolecular forces and intramolecular forces. The intramolecular forces are forces between the molecules, so the bonds, right? The ionic and covalent bonds, these are intramolecular forces. But if you have a H2O molecule here and an H2O molecule here, they're also going to attract each other. These are intermolecular forces, right? So the intermolecular forces are going to determine the physical properties, right? So one rule that I tell a lot of people is use this rule: like dissolves like. Like dissolves like. What does that mean? It means that if you have a polar molecule, it will dissolve in polar molecule. If you have a non-polar molecule, it will dissolve in a non-polar molecule. This is why water and oil don't mix, by the way, right? This is because oil is non-polar, water is polar, right? So oil will dissolve in something that's non-polar, right? Ammonia in water, for example, is an example. If I give you ammonia and water, are they going to mix? Yes, we already know that they are both polar, right? But what about ammonia and CH4? They won't mix because CH4 is non-polar. So like dissolves like. So this is an example of an interaction between water and ammonia, and these interactions, we call them hydrogen bonds. But we'll talk more about hydrogen bonds in the future. But this is why they mix. All right. Okay. So it's, yeah, like we said, water and oil don't mix, and because water is polar and oil is non-polar, right? Okay, so another physical property is boiling and melting points, right? So these to boil something or to melt something, right? It's going to require to break the bonds between the molecules. So if the bonds are stronger, it's going to be harder to boil and melt, right? So the greater the force, the harder it is. That's why solids, it's really, really hard to melt a solid, right? It's hard to melt a metal, but it's easier to melt, ice. It's easier to melt, liquid because it's already melted, right? And it's easier to boil a liquid, things like that, right? So attractive forces affect this. But also another thing is we talked about this, but this is why ionic compounds are harder to melt and to boil. So ionic compounds have higher boiling and melting points. All right. And this is a table of an example giving you, showing you that, look at the bottom here. NaCl and KBr are ionic compounds, and they have really, really high melting and boiling points. Look at what's next. It's H2 and NH3, polar compounds, right? Polar compounds will have more forces. So we start with ionic, then we go to polar covalent, and then we go to covalent. And this is important because guess what? I'm going to give you different compounds and I'm going to ask you to rank them depending on their increasing or decreasing melting and boiling point. And you're going to say, oh, this one is ionic, so it's going to be the highest. This one is polar covalent, so it's going to follow. And this one is non-polar covalent, it's going to be the lowest. All right, I think that's enough. That is enough for this chapter. I will see you next time. Bye bye.